In this class, we are going to use a basic demonstration in order to understand the concepts behind the working mechanism of optical fibers and some phenomena that contribute to the degradation of the signal inside the fiber as the light propagates. The only fiber that is going to be observed is a polymer one. Optical fibers can be made from other materials other than glass, but this polymer fiber suffers from space light scattering in terms of the direction of propagation. Also, these are highly affected by attenuation factor, meaning there is absorption by the fiber itself. However, this is only critical in long-distance communication. This fiber does not have cladding, but with the material's refraction index being approximately 1.4, the air itself around the fiber works as cladding, having the wave-guiding effect. To simulate the nucleus of a fiber, acrylic rods were used. Thus, the condition for total internal reflection is achieved, the nucleus with a reflection index bigger than the cladding, which is the air. For the light sources, two lasers were used, a red and a green one, and also a white LED. In the end, the cladding effect was seen by changing the medium to water or glycerin, turning them into the cladding materials. The cladding affects the critical angle, that is, the total internal reflection angle. The first thing that was seen was the light scattering. This light scattering is related to the alternation of the light's course as it goes through a certain material. It can be called, for simplification, a space light scattering. This can happen due to different reasons. For instance, if there is a defect on the fiber. In this type of scattering, the Rayleigh scattering, it inversely varies with the wavelength. This is a natural effect that always occurs. There is another type of scattering that affects the direction of propagation of the light inside an optical fiber, associated with the surface defects, which is the Mie scattering. A scratch was made on the acrylic rod to see the effect of the Mie scattering. Inside the fiber, when the light comes, as long as it's within the critical angle, the incident angle is equal to the reflection angle. This only if the surface is perfect. If the surface isn't perfect, the normal will change in the region of the defect, which leads to a different reflection angle. From that point on, if the rest of the fiber isn't perfect, the light can travel with an angle inferior to the critical angle, leading to part of the light being reflected but the other part being transmitted. This means that the Mie scattering can result in the loss of the amount of light, less signal's intensity. The light scattering contributes to the signal's attenuation, either the Mie or the Rayleighs. The absorption of the light by the fiber itself also contributes to the attenuation of the signal. The absorption can happen due to the fundamental absorption of the material of the fiber. If it's silica, fundamental absorption of the silicon-oxygen bonding starts to happen for IV radiation. There are also two other absorption peaks at around 1.4 and 1.24 micrometers related to the OH bonds that result from gases used in the fiber fabrication. All of these combined, absorption and scattering, result in attenuation, the lowering of the intensity of a light pulse when traveling inside an optical fiber. Attenuation is divided in intrinsic and extrinsic. The intrinsic is the dispersion and the fundamental absorption. The dispersion itself can be the Rayleighs or Mie. The extrinsic is, for instance, bad handling of the fiber. Another high-level phenomenon that happens in optical fibers is temporal dispersion. Temporal dispersion is when the light pulse has a certain duration at the entrance and a different at the exit, being a larger pulse. Temporal dispersion can be of two types, intramodal and intermodal. Intramodal is considering only one direction of propagation of the light. When the light source is not pure, the light is going on many different wavelengths, and as the speed of light varies with the wavelength, in reality, even if all the light is going in the same direction, it is going in different speeds, meaning the pulse with a certain duration at the entrance will have a different duration at the exit. In intermodal, inside the fiber, there are more than one direction of propagation for the light. When this happens, even if the different directions start at the same time, the longer path length has a longer propagation time. For the setup, firstly, the lights of the room were turned off to better see the previously mentioned effects on the fiber. With the lights off, the Rayleigh's effect was visible by seeing dust particles bright. These particles appeared bright because the light, even though the laser is completely directional, suffers scattering, changing its direction. It is Rayleigh's dispersion. As it is an elastic dispersion, it does not change the energy of the radiation. To start, a solid-state red laser was used for the light source. This laser is an old laser made from helium and neon. With the light from this laser pointed directly at the base of the acrylic rod, the wave-guiding effect of a light beam inside the fiber was observed. The total internal reflection could be seen as well as the wave being guided inside the optical fiber. The light dispersion could also be seen as the dimension of the beam was smaller in the beginning of the fiber and got bigger along the fiber. Also, by changing the incident angle, it could be seen an increase in the number of reflections and vice versa. After, the effect of a green laser was seen. This laser was more visible, however it had a higher scattering. As long as the light traveled inside the acrylic rod, the light was more scattered, which means that it travels in different directions from the main beam. This was responsible for different reflection angles and led to some of them not promoting total internal reflection and consequent intensity loss. Another condition that contributed to the intensity loss was the surrounding medium, the cladding. When this has a higher refractive index, such as a human finger, total internal reflection is not possible anymore, thus the light escapes from the fiber. The quality of fibers dictates the scattering losses. Every shiny spot observed corresponds to a defect. If the defect is on the surface and if the light's focus is there, a big amount of light will be lost in that spot. Even in a single mode, there is space scattering due to the defects present in the acrylic rod. When the fiber was observed from the top, there was too much scattering that appeared to be multiple signals in that segment. To observe the multiple mode, a white LED was used. Also, it was possible to observe the waveguide effect provided by the optical fiber. However, in opposition to the laser, the LED has emission in multiple wavelengths, so it was not possible to observe a single beam inside the optical fiber. Despite that, the light reached the top. To observe the external attenuation, the polymeric optical fiber was utilized, which was bent at the end. When the light reached this segment, there was a big intensity lost, and it was possible to watch a strong light emission. This effect happened because the light, when it reached the bended part, started to travel at a lower angle than the critical one, which caused the scattering and transmission of the light after the segment, and it was responsible for signal attenuation. To observe the cladding effect on critical angle, materials with different refractive index were used. All the refractive indexes are for a wavelength of 590 nanometers. First of all, the refractive index of the acrylic rod is 1.495. When the cladding corresponds to the air, its refractive index is 1. The critical angle is very small. This means that almost every incident angle promotes total internal reflection. Next, we inserted the acrylic into water. This simulates a higher cladding refractive index since the water refractive index is 1.33. This implies that the critical angle is higher than in the air. For incident angles lower than the critical one, there was a big portion of the light that was lost from the fiber. However, the light is refracted closer to the interface between the acrylic and the water, which indicates that the cladding has a lower refractive index. As long as the incident angle was closer to the critical one, it was possible to observe total internal reflection. After that, the simulated cladding was glycerin, which has a refractive index of 1.473, that is closer to the acrylic that has a refractive index of 1.495. The glycerin had an orange color due to a process that it was subjected to, but it helped to observe more clearly the light scattering. As expected, the incident angle needed to be higher to promote total internal reflection. When that did not happen, the refracted light had almost the same angle as the incident one, but a small shift due to the interface between both mediums resulting from the similarity of refractive index. Additionally, the intensity of this refracted beam was very high. It was also possible to observe total internal reflection between the air and the glycerin due to the higher glycerin refractive index. In summary, to observe total internal reflection, two mediums are needed, a cladding and a core, and it is the working principle of optical fibers. The material where the incident light hits is the core, and it should have a higher refractive index than the other medium, the cladding. The changing of the cladding material will change the critical angle, which means that the higher the cladding refractive index, the higher the critical angle will be. If the cladding material has a similar but lower refractive index compared with the core, as in the case of acrylic with glycerin, when the incident angle is lower than the critical one, the transmitted beam will present much more intensity than in the water under the same conditions. Given that, the reflected light will have lower intensity in glycerin. That is all for today. Thank you very much for your attention.